Welcome to this overview video of the Rates 2 topic. This is roughly corresponding to a chemical kinetics course in the second year of UK A-level, and the aim of this video is just to understand in overview all the ideas in the course. Here are some of the key terms that we're going to be coming across. Okay, so rates of reaction. Chemical reactions can take place over a vast range of timescales. So very fast reactions, reactions involving ions. So this reaction here between sodium chloride and silver nitrate, producing a silver chloride precipitate here. And this is effectively just a reaction which involves a silver plus ion combining with a chloride ion to form that precipitate, and that's an incredibly quick reaction. Other examples of very quick reactions would be these kind of explosive reactions that take place. Around about the middle of the time scale, there's typical types of reactions we might actually measure the rates of reaction of in a lab. This is a piece of magnesium ribbon, which is reacting with some hydrochloric acid. So that's the type of reaction which might be over, for example, in a minute or two. On the slower end of things, thankfully, rusting is a very slow chemical reaction. And here we've got corrosion of statues by acid rain, again, a mercifully quite a slow process. Now, chemists are really interested in speeding up chemical reactions. So one of the most marvelous reactions that we know about is photosynthesis. And this is essentially taking some carbon dioxide and some water and turning them into glucose and oxygen. And we'll just balance that equation up. And this is a chemical reaction which is strongly endothermic. And so if we represented it on an energy level diagram here, we would have these reactants here. The products would be a much higher energy level. And we really need to put some energy in order to be able to get this reaction to happen. However, this energy comes in the form of light. So visible light comes in here, or UV light really. And the photons of UV light are able to provide this extra energy in order to get this reaction to happen. But that might lead you asking the question, well, why don't carbon dioxide and water just combine outside? There's plenty of UV light. Why does it need plants? And the answer is that in here we have a catalyst, or in fact many sophisticated catalysts within membranes that are called thylakoid membranes of chloroplasts, and they are actually catalyzing this reaction, chloroplasts. And so this activation energy for this reaction is currently pretty high, so the reaction is very slow, but plants have catalysts within them which are able to reduce that activation energy and make this reaction happen at room temperature. Now, why is this of relevance to us? Well, one of the big reactions that in our day we really want to be able to speed up is the following reaction, the splitting up of water into two molecules of hydrogen and one molecule of oxygen. Now, hydrogen here we'd really love to be able to use as a fuel in vehicles, because when it burns in oxygen, it just produces water, so there's no greenhouse gases that have been, well, no carbon dioxide at least that's been produced. The difficulty is that in order to do this reaction, again, it's endothermic, and so we need a large amount of energy input, and that's typically provided by a battery or some other source of an electromotive force. But then the amount of energy you need to get the hydrogen out is then roughly the same as the amount of energy the hydrogen gives you back. So you're not really gaining much. You're still having to potentially burn fossil fuels or do something to generate that electrical energy. And so wouldn't it be wonderful if instead of using that energy, we could instead just use the energy from the sun? So wouldn't it be great if UV light would be able to supply the energy for this reaction? And it can. The only problem, again, is a problem of activation energy. And so we want to be able to speed up that process by providing catalysts. A sort of quite a primitive one is titanium dioxide. And now they are developing better and better catalysts. A promising one looks to be sodium tantalate with lanthanum as a dopant in that. So feel free to do a bit of research and find out about that if you're interested. But these are catalysts, so they are lowering the activation energy and making this reaction faster. Big business in industry. In other cases, we want to slow processes down. So, for example, we might want to inhibit rusting, stop that from happening. Or this is a picture of a bacterial ribosome. These are the molecular machines inside bacteria that help them to make proteins and hence divide. If bacteria divides, then it needs new proteins to form the new bacterium. Then if that's the case, then if we want to stop bacteria from invading a host organism, then a good way of doing that is to try and stop them from making any proteins. In other words, we want to inhibit this ribosome. We want to stop it from making proteins. And so in both these cases, we want to actually slow down processes that are happening. So where does this leave us in terms of the importance of kinetic studies? Kinetic is just another word that means essentially the rate of reaction. So rates studies. And the big question is, what is the mechanism of the reaction? So let's say, for example, just thinking about a chemical reaction just from a reactant to a product. Well, this could just take place in one step, or it could take place via an intermediate. So it could be that a reactant here, for example, maybe two of the reactants combine together to form an intermediate, and then maybe that intermediate then subsequently breaks apart to form two product molecules, for example. So this could be a two-step mechanism. And why is it important to know the mechanism? Well, it's important to know the mechanism for two reasons. The first being that each of these individual steps, if it takes place by multiple steps, will have potentially different activation energies, and therefore we could find out through the mechanism which one of these steps is actually key. So if we want to design an inhibitor, then maybe we're better off going for the step which is a little bit slower in the reaction. And the other thing the mechanism tells us is exactly what the molecules are doing. So we don't just want to know the steps of the process, but say we were thinking about the ribosome here, we want to know the actual shape changes that are occurring. Now, kinetic studies won't tell you all of that, but they do tell you something very important. And I'll show you how now in a second. So, and the center of really this topic is something called the rate equation. So for this very simple reaction here, what they're saying is the rate of reaction, which we define as the change in the concentration of the reactant with time, either the negative of that or the change in the concentration of product with time. And we can relate that actually to the reactant concentration. There's a proportionality constant involved, the rate constant, and a power here. Now this power up here is known as the order of reaction. And effectively what this is saying is how much does concentration affect the rate of reaction. If this number is very big, then a small change in concentration will have a big effect on the rate. If this number is 0, it will have no effect at all. And this order of reaction is basically linked to the mechanism, because the order of reaction tells us how many molecules of R in the slowest step of the reaction. Now that's a little bit of a simplification, assuming that one step in the mechanism is the one that's actually going to effectively slow the whole reaction down. It's no so-called rate determining step, but for our purposes that's what we're looking at. So that's what the order of reaction tells us. Now this quantity here is called the rate constant. And the rate constant for this reaction is effectively telling us it's essentially decoupling the effect of concentration from everything else. So this is concentration independent. And that's great, because if we want to compare reactions that are taking place under different concentrations, then really we want to be comparing a rate constant which doesn't depend on concentration. So it's concentration independent, and it's also linked via something called the Arrhenius equation to the activation energy for the given steps in a reaction, and it's got all the temperature dependence of the rate in as well, so really powerful to know these quantities. So those are the two big players that we're going to be thinking of mostly in the topic. So finding reaction orders, there's effectively two big ways of doing this. Continuous monitoring experiments, and what that means is you just take a reaction, proceeding over time, the reactant concentration is going to drop, let's say something like that. And effectively what we can do with this is determine the rate just by the gradient of the graph. So we can take the gradient at that point, we can take the gradient at that point, we can take the gradient at that point, and so forth. And we could determine the rate of reaction at many, many different concentrations. So this might be concentration 1, sorry, concentration 1. This is concentration 2, and this is concentration 3. And it turns out that if you plot the rate of reaction against concentration, which is exactly what this equation is saying, rate versus concentration, then you're going to get a different shape of the graph depending on the order. So I won't spoil all of the future videos, but for example, if you got a plot that was concentration of reactant here and rate, remember, is the slope here, and we just got a lovely straight line like that, then that's effectively a linear function. The value of r is 1. This is r equals 1, and we call this first order reaction. So that's how we're going to do it using continuous monitoring. The other way of doing it is using what's called an initial rates experiment in this case. So if you imagine an initial rates experiment, that's effectively taking the slope right at the beginning here. So I'll just draw a tangent on right at the beginning of the reaction. So this is the initial rate of reaction, when the reaction is fastest. And effectively what you can do in these initial rates experiments is lots and lots of different conditions, and you get different initial rates. So for example, let's just quickly here. So I might choose initial reactant concentration, and this is the initial rate. And let's say I chose initial reaction concentration of 1, and then I do it again with a rate concentration of 2. In this case, the rate, let's say, was 1, and imagine now the rate is 2. So what I've done here is I've doubled the initial concentration, and I've doubled the rate. So what that means is I've got an example of direct proportion here. So in other words, r equals 1. So the order is 1. However, if I'd done the same thing here, and instead I'd got, let's say, 4, then I've now got, instead of that, I've got times 4, which is times 2 squared. So in other words, when I've doubled that, I've multiplied this by the square of the factor I've increased by. So in other words, I must have an order of 2. So depending on how the initial rate varies with the initial concentration, we can determine orders in that way. What about the rate constant? Well, remember the rate constant is just linked to the rate by this equation here. Once we've got the value of little r, which we've got to determine experimentally, we can simply rearrange this to find k as the following equation. So if we know little r experimentally, we know a particular concentration, and we know the rate at that concentration, say for example as a tangent, or maybe it was an initial rate, an initial concentration, we can simply calculate this quantity here very easily. Now, how do you then go from the rate constant to activation energy? Well, it turns out that a wonderful Swedish chemist called Svante Arrhenius worked out this relationship exists between the rate and some other quantities here. So watch the full video to see what these are. But effectively here, this is what's called a pre-exponential factor. That's something to do with essentially the frequency at which collisions are taking place. It's basically a constant. Now R here is just the gas constant, 8.31 joules per Kelvin per mole, and temperature is in here. So we see here that the rate constant is dependent on temperature. That's why rates of reaction get faster when temperature goes up, because as temperature increases, K will become bigger. Pause the video and think about that, or watch the full video on the Arrhenius equation to see why. But how can you determine the activation energy? Well, if you measure the rate constant at different temperatures, then the rate constant is going to change, and it's going to change depending on the activation energy. Now, it's going to be really hard to actually make a graph to actually work out the activation energy, but if we take the natural logarithm of both sides of this equation, then we get the following relationship. Natural log of anything e just simply becomes whatever the exponent actually was, rt. So if I just rearrange the right hand side a little bit more, give you that. Now we've now got an equation here which is in a lovely y equals c plus mx form. So if we plot 1 over t as along the x-axis and log k on the y-axis, we can get a lovely straight line graph. So this is 1 over t, that's ln k. We get a lovely straight line graph. It's going to have a negative gradient because the activation energy is positive. Let's do a reaction here. We're going to plot a few points. We're going to draw a best fit line going through them. And we're going to find that the slope of that best fit line is minus EA over R, and as R is a constant, we can simply work out the activation energy from that plot. Very, very nice.